You have a class?
Yeah. All right. Well, seems like just us three here. All right. Any questions from anyone? Okay. So to continue where we were last time, I guess let's start discussing, right, the topic of Black-Scholes PDE. So first of all, right, Black-Scholes PDE is an idea, right, an equation that connects, right, the Greeks of an option. Well, I want to say this, I don't want to write down the equation right away. The reason is what you've been seeing so far in your homework is the Black-Scholes PDE for European option, all right? But the idea of Black-Scholes PDE is more general than that. We will be talking about exotic options soon and also American option. And you will see that there, right? The PDE, the Black-Scholes PDE is not the same, okay? It's not exactly the same as the one that is in European option. That will be changed. And so, and also I want you to kind of appreciate the point, right, of the PDE itself. So basically, right, for now, just think of it as an equation that connects the Greeks. And because of the nature, right, of the, well, and of course, right, is deeply connected with Ito's formula, right? And so because it's deeply connected with Ito's formula, that's the point we want to discuss today. Basically, the Greeks that usually show up, right? The Greeks are usually involved are the theta, right? Delta and gamma. I mean, there might be more than that, all right, as you will see with the exotic option. But the ones that are guaranteed to show up are these guys. So, okay, on one hand, right, it does connect the Greeks, right? It connects these guys. On the other hand, right, it does not connect all the Greeks, right? And if you look at the Wikipedia page, right, there are like, I don't know, at least 10 Greeks, right? So the ones that the Black-Scholes PDE care about usually are these guys, again, right, because of its connection to Ito's formula. Of course, right, it also, well, maybe let's not forget, it connects the Greeks, but also it has the option price, right? So maybe if it doesn't connect the option value, then that's perceived, you know, that's conceivable, but that actually might be a little bit missing, right? So it connects the Greeks and the option value. Okay, so right after that, maybe let us write down, right, the typical Black-Scholes PDE for European option. For Euro option, right, the Greek will be this. Oh, we get more customers. Oh, no problem. I was thinking this poor gentleman will have to sit here with me. Okay, so for European option is always this. Now, so again, right, let us see what's going on. So this is the option value, right? This is the option value. This is the theta, right? I mean, I think so again, right? So typically speaking, theta is the derivative with respect to the time to maturity. So basically the duration, right? The time left. So basically tau, technically speaking, is t minus t, right? Again, I mean, I don't know. I never know a official definition for this, but first of all, you see why, right? They don't care to differentiate with respect to little t, because these are financial concepts, right? You want to know how it changed with respect to time left, right? Duration, rather than the current time. That's mathematics, right? That's not financial. But on the other hand, you can easily see that by chain rule, right? These guys are almost the same with the difference of a minus sign, right? So Wikipedia defines like this, and probably if Wikipedia defines like that, probably that's the official definition. So anyway, right? Lucky for us, by the chain rule, it is equal, right? So no worries. But at least you should appreciate the difference in the meaning, right? The theta is supposed to measure the change of the option value with respect to time remaining with a minus sign, right? Not really with respect to little t, but. And this is our delta, and this is our gamma, right? Okay, and this is our stock price, right? And by the way, this is a lazy way, right, to write, V of time and the stock price at that time, right? This is a lazy way to write the stock price at that time, meaning that this equation holds at any moment, right, in any price, as long as you are, you're up to the expiration, right, like that. Okay. Now, of course, you can read it however you want. Usually PDE is written, right, so that the right-hand side is equal to 0. But if you want, you can pull all the Greeks, right, on one side and put the option value on the other side, right? It's the same thing. Okay. Now, so there are many things to discuss, right, about this. First of all, why is this true? And of course, right, actually, here is a deep message, by the way. When you enroll in this program, right, we used to require the students to know PDE, right, or have taken a PDE course. And the reason is exactly because of things like this, that you will have to deal with PDE one way or another. But like, the way you have to deal with PDE is not exactly in the, how to say that, in the PDE literature direction. So we eventually dropped that requirement. But right, the point is, right, the PD does show up. And so first of all, the point is, right, you want to understand what this is trying to tell you. And the second, right, is that why is it true? Well, so it goes all the way back, right, to this whole martingale theory, right? So let's start with that. So the martingale theory, right, that I kind of discussed it, right? So this is similar to Brownian motion and Ito integral, but it's more general than that. So instead of WT, you can think of MT. All right, and what I told you are more or less true, but let's just go back and see what happens. So suppose that you have a martingale. All right, what does that mean? What that means is when you take expectation, you take conditional expectation, right, is equal to past value. Okay. Then because of something like this, you can kind of think that a continuous martingale continuous means, it does not have, when you plot the path, right, it does not have jumps. The reason is when you have jump, you can cheat and, make your path a little bit nicer. So basically continuous means the path is continuous. A path continuous martingale will have its path almost everywhere non-differentiable. Again, right, we said this for Brownian motion. It's the same thing for a martingale in general. All right. So we won't go through why this is true, etc. But just take your intuition with Brownian motion and trust that this is true. The next thing, right, is this, that then, right, you will ask, how do you integrate against a martingale, right? Here, this is the change in the martingale, right? This is the number, right, of shares of the martingale, if you will, right, that you hold at this time. So basically, you can try to think of this as a betting scheme, okay? A betting scheme. Just mathematically, you don't have to care. But if you want to give a financial meaning to it, right? How does this work? I think Cesar tried to tell you this at one point. Basically, right, you think about it. Suppose that, right, you bet, I don't know, $10, right, at time S. What are you betting against? You're betting against the change of the martingale at that moment, right? If like the martingale, so right, at time S, right? Let's say you bet $10. So what are you doing, right? If the change, right, is going to be, let's say, +1, then the integral returns to you 10, right? Then the change in the integral is 10, right? But if the martingale turns up to be -1, then the change is -10. So you lose $10. Does that make sense? And then, right, the integral means you just add up all this net change to get your overall, winning. Is that okay? So the integral right here represents a betting scheme, right, against a martingale. Now, again, right, it really, okay, if you really want to make it more concrete, right, you think of it as a random walk, right? So a random walk, meaning, right, xk is a sum si, I from 1 to k, right? Where si is iid, 1 with probability 1/2, -1 with probability 1/2, right? So you understand what happens, right? This is basically step right or step left, right? You start at 0, you go right with probability 1/2, and you go left with probability 1/2, right? Okay. Now imagine what you are doing when you do something like this. Right? So this looks complicated mathematically, but what are you doing, right? Is imagine you're at a casino, right? At any time point, the casino will ask you, well, do you think, right? By the way, right, the delta xk, right? You know what it is sk plus 1 minus sk. Oh, sorry, xk plus 1 minus xk, right? Which is just sk, right? So at any time point, the casino will ask you, do you think, right, the random walk will go right or go left? Yes. And how much do you want to bet on that? Okay. And suppose that you bet $10, right, on going right. And if it does go right, then you win $10 for that particular bet. If you bet $10 and it goes left, which is -1 here, then you lose $10 for that bet. And if you keep summing up, that's your net fortune. Yes, throughout the whole game. Is that okay? And so there's nothing very special about this kind of structure of the thing, right? Now, again, this is what trader does as well, right? Instead of xk as a random walk, think of xk as a stock. And this is like the return or something, or lot return, whatever, then what does the trader do every day, right? They try to guess if the stock will go up or down tomorrow. And then they place how many bet, right? How much they want to buy on that stock or how much they want to short on that stock. So basically a integral against a stochastic process, right? Against a change is really, I mean, again, there are many ways to interpret it, but financially it's a betting scheme against that thing. Now, in financial theory or in stochastic theory, we want to make this into a martingale to make sense out of it. But right, like you see, this doesn't have to be a martingale itself. But right, the punchline is this: that the integral against a martingale is a martingale, as long as the betting scheme is bounded properly, right? And I won't comment on what bounded properly here means, but basically, you know, it's L2 integrable, etc. Again, right, the point of this course, I don't want to go too deep into the math theory. You lose the perspective. I want to give you the perspective, and you can go learn the math if you are interested, right? So what is the message here, right? For example, in this kind of scheme, again, I think Cesar tried to discuss this, right, a couple of weeks ago. The point is this, that, right, you think about, and this is connected to the so-called St. Petersburg paradox, right? I do believe this kind of question does show up on an interview. I think I saw this as an interview question. You remember, like Dan Pujol, right? He talks about the interview textbook that you can take a look. I think, right, this kind of question does get put in those books once in a while. Honestly, I don't know what the answer is supposed to mean, right? So for interview questions, there are something that you think is right, and there's something that the interviewer wants to hear. You better answer as the interviewer wants to hear, right? If you want to get a job. So sometimes I know what the answers the interviewer wants to hear, sometimes I don't. This question I don't. I understand the meaning of it because I have my own interpretation. But if you want to, right, take a look into those books and see what the interviewer wants to hear. But basically, right, what's St. Petersburg's paradox is exactly about this kind of thing, right? It says that if you have, so, you know, it usually phrased as you flip a coin, right? Flip a fair coin. If it's head, you gain $1. If it's tail, you lose $1. Is there a sure win scheme, right? A sure win scheme against this, right? Is what? Double betting, right? What does that mean? So you start out, right? You bet, I don't know, $1, right? If it's, say you always bet on head, all right? If it's $1, if it's head, then you win $1, right? If it's tail, you lose $1. Well, so what? What's the next turn? If win, quit, right? If loss, what do? Bet $2. Why? Because if you bet $2 now, if head shows up, what's your net gain? Your net gain will be $1, right? 2 minus 1. Whoops. Quit. If lost, what do? Bet 4. Right? Because if you win, how much do you win? 4 minus 2 minus 1, which is $1, right? So the idea, right, is very simple. Because 2 to the n minus the sum 2 to the I from 1 to the n minus 1 is, I guess, 0, right? It's always 1, right? So this is your win on the nth turn. If the head shows up, this is your loss, right, on the previous turns. And the head must show up at some point, right? So that's going to be sure win. Okay? Understand? On the other hand, right, notice that like I said, this is a embedding scheme, so it can be embedded into a martingale, right? This, right, so the net gain can be the sum, right? But what is the phi k here? Your phi k is where phi k, as we say, is 2 to the k minus 1, I guess, right? Depends on how you sum it. If you sum from 0, then it's going to be 2 to the k, right? I guess indicate a function, right? That k is not head, right? Or something like that. Or I mean, there's something about head, right? Not showed for 1, for 0 up to k minus 1. You understand? So right here, basically, this captures the above description, okay, in an equation. Which exactly you see it will show up like this. Because, right, delta xk will be minus 1, and then until 1. Got it? Okay. So again, right, I mean, I think the paradox, if you look at it, I feel like, if I remember correctly, the paradox is phrased so that the expectation of the game is somehow infinite. I don't care about that. So you can read the paradox that way, right? Usually, I think the paradox is read in such a way that if you look at this, somehow the expectation comes out to be infinite. The paradox, as far as we are concerned, as I am concerned, is it flies in the face of this thing. An integral against a martingale is a martingale. Okay. By the way, right, casino, I think, does rely on this a little bit when they operate. Why? Because if they have some sort of like a martingale scheme, all right, then doesn't matter how you bet, you cannot win against them. Yes. Except, right, there's this thing. So that's why, right, the mathematics is that you must not be able to double bet. By the way, right, this actually does have practical application. If you, I hope you guys don't go to casino too often or never, but if you go to casino, there is a rule in casino that you cannot double your bet after 5 times or something. You can at most double your bet 5 times in a row, and then you have to go back. So if you look at casino are deeply aware of this kind of math, all right? But anyway, so this is right what we're dealing with, all right? So just telling you this, right? And so what do I want to say here, right? So back to the whole martingale theory. So this is the backbone of martingale theory, that if you integrate against a martingale, as long as you don't cheat, it's still a martingale, all right? Now, how does that have to do with us? It has to do with us like this, right? So consequence for us. Any question? Question? Right? So consequence would eat those formulas like this. Suppose you have M, right, a martingale, and you have some function of M that for some reason you also know is a martingale. All right. What's the consequence? The consequence is this, right? If you do Ito's formula, right, on this function, then what do you get? You got this dt plus this dm, right, plus 1/2 this quadratic variation, right? Okay. Now, you don't know, I mean, well, usually this will be something square dt, right? But generally we just leave it like that. But what happens? What happens is this, right? You know, this is a martingale, right? So this is a martingale. You also know, sorry, this is DMT, right? You also know that this is a martingale. Why? Because of this. So this is also a martingale, right? What does that mean then? What that means that these guys cannot cause trouble. Okay, because if these guys somehow fluctuate up or down, remember, right? Actually, basically the point is this guy is deterministic because it's dt. This is also something dt, right? Let's say sigma squared dt usually, right? So the point is this, right? You know, the whole point of martingale is what? Sometimes it can be positive, sometimes it can be negative, right? Think of random walk, right? The whole point is, right, if you keep always going right, then you cannot be a martingale because you're always going up. The whole point of martingale is sometimes you go up and sometimes you go down. dt, right, cannot be martingale because it always go up. Therefore, if you have a martingale like this, a martingale like this, what happens is this must be true, right? The part that kind of interfere with the martingale must die out if this is truly a martingale. All right. So that's the kind of like the iron, right, rule that has to be enforced, coming from the fact that when you integrate a martingale against a martingale, right, you have a martingale. All right. Questions so far? By the way, right, this is not as strange as it seems. What do you think the equivalence of martingale is in the regular world, in the regular calculus? In the regular calculus where you have no stochastic process, then what is a martingale? Constant. Okay. I'm sure you have learned about sub-martingale and super-martingale from Professor Larson. So sub-martingale is a generalization of increasing, and super-martingale is going to be generalization of decreasing function, right? So I won't go too much into it, but basically, right, with constant function, you really just have a constant. With a martingale, what do you have? With a martingale, what you have is constant on average, right? That's what happens. You have constant on average rather than constant. But notice, right, that if you have a function that is constant, what must happen? Its derivative with respect to time must be 0. So that's your ODE, if you will, right? So this is nothing that's strange. That's all I'm trying to say, right? This is just exactly the enforcement, right? It just says something that, yeah, kind of common sense, that if you have to be average on constant on average, then the things that push you up and down must be 0, right? That's what it says here, okay? All right, so now let's see in the Black-Scholes model, how does that work? So in Black-Scholes model, right, first of all, let's forget about, or actually, let me just do, it's not in Black-Scholes model. In pricing framework, it's more general than that. So in pricing framework, right, you can start with any model you want, but we know that this must hold. Let's say U, right? Sorry. Let me do this. when you price the future stock based on the current information, you must get the current stock, right? This is for U, T less than U. What this means, right, is that e to the minus RTST is a P tilde martingale. Doesn't matter what framework you adopt. This is true, right? So then, right, how do you price something? If you have something as a European option, right? We are discussing Europe option. Then the pricing formula just tells you to do this. But what does this pricing equation tell us? This tells us that, well, guess what? The discounted option price is also a risk neutral martingale, right? Because you put this over here, you get that. Do you understand? So in pricing framework, basically it says that the discounted anything is a martingale, right? Almost. But I mean, you got to distinguish this. So you start out calibrating the model or finding the risk neutral probability by saying that the discounted asset is a martingale, is a risk neutral martingale. Then, right, you use that to find the option value. But, right, the consequence of all these things is that discounted anything is a martingale. Discounted price process is a martingale. Well, what's more though, right, is this, that by Markov property, again, we kind of skip a lot of things here, but I mean, assuming that the stock price is Markov. If you assume that basically, right, we did not discuss what model you use, but if you use a model so that the stock price, right, today condition on yesterday only depends on the stock price yesterday and doesn't depend on the history of the stock, right? Then the option value, let me do a little v, right? And the option value can be thought of as a function of time and the stock price at that time. Okay, now this is deep, all right? This is deep, pay attention. Again, we skip many things, but we are saying, right, for a euro option, the option price is really just a function of that time and the stock price at that time and nothing before that. Now, this is important. Why? Because this can be easily violated in two ways. The first one, let's say it right away. If V is not European, meaning in exotic option, you won't have this, right? If you have a option that depends on the whole path, then at any time it depends on the previous path. So the structure of the option will destroy it. But here is a European option, so you still have this. And the second, so we will see this right later on in this course. The second you won't see in this course, all right? But I just want you to keep it in mind. If the stock price is not Markov. So this actually will be a complex extension of the Black-Scholes. Meaning now you say the stock somehow behaves that has a long-term memory, right? The stock somehow remembers, right, its past history to decide its future movement. So that is not in this course, right? We don't discuss non-Markov model, but that can happen, all right? Anyway, going back to this, right? That suppose you have this very pretty, right, representation. Again, if you want, think Black-Scholes formula, all right? Right, the Black-Scholes formula exactly highlight this, even though, right, in a complicated formula, but still. Now, once we have this, guess what? We are in business, right? But of course, be careful, right? This guy itself is not a martingale. But what is a martingale? This is a martingale, right? From here. So what do? Well, exactly, right? We apply Ito's formula to check out its components. So by Ito, right, you do D of this, right? Now, notice that there are two parts where T plays here, right? Little t. It shows up in here and shows up in here. And so that's why when you differentiate with respect to little t, you got minus R times V plus V sub t, right? Okay. And then you got V sub x, right? ds plus 1/2 V sub xx, right? D. And suppose that we are in the Black-Scholes framework, then we got sigma squared dt, right? All the time multiply with e to the minus RT, right? Because that's the factor outside. Sorry, I'm doing something. There's the dt here, right? There's dt. Is that okay? Right. So now you look a little bit more into this, right? Black-Scholes model say that this is going to be R STDT plus sigma STDW tilde T, right? Okay. Now, let the dust settle, and what do you know? You know this is a martingale, right? From here. You search and search and search and see on the right-hand side, what do you know? On the right-hand side, you know that this part is a martingale. Why? Because W tilde is a P tilde Brownian motion, so it's a martingale. So this is a martingale. Only this part, right? Well, then what do you know? Then the rest of the part cannot interfere, right, with the martingale structure. Meaning they must be 0.
Can I ask a question?
Yeah.
So you said the price process discounted back is a martingale earlier?
It's a risk neutral martingale, right? It's not a physical martingale.
Okay, because in the thing that you circled,
yeah,
it's multiplied.
Unfortunately, right? I mean, we could, but in the thing I circle is the Brownian motion part.
Mm-hmm.
But you notice, right? Why is this a martingale? Right? Why is this a martingale? The reason is because when you do this with Ito's formula, you will get sigma STDW tilde T. You understand, Kareem? So in fact, right, this guy does show up indirectly in this. So instead of writing this, I write this.
Okay.
I think in your mind, you're thinking something like this. You're thinking, is this a martingale? Or something like that.
Yeah.
The answer is no, because it's not D of the martingale. This is E to the minus RT times D of this, right? The stock price itself is not a martingale. Do you understand what I'm trying to say?
Yeah.
So it's subtle, right? This is you know, like basically, if ft is a constant, then dft is equal to 0. But some other function times, you know, sorry, if e to the minus rt, ft is a constant, then d e to the minus rt ft, right, like this, is equal to 0. But e to the minus rt dft, right, is not, because you're not doing product rule. You understand what I'm trying to say?
Yeah, I see.
Right, like that. So, right, so we use that implicitly in here because that's exactly that. Okay.
Thank you.
Anyway, right, so you see that we have got our Black-Scholes PD out. And notice, right, that this argument is highly universal because I did not use any structure of the function phi, right? It can be butterfly, it can be put, it can be call, whatever you want, okay? It really comes from the pricing structure. It doesn't come from what phi is. On the other hand, right, notice that in the homework, I want you to play around with the structure of the phi. So I ask you to not use the abstract argument, meaning this argument, right, for the butterfly and the put. I want you to use the linear dependency between the options, all right? But I do admit that this is universal, meaning that this argument works for any European option. But in the homework, I want you to be more concrete by checking out the structure of each of the option, right? And see that it works. So what do I mean by this, right? So first of all, right, any questions? So you see this is true, right? Now, let's check out the PD, right? So first of all, if we have a call option, right? In other words, this is going to be st minus k plus. Then you have concrete formulas, right? Whoops. You have concrete formula v sub t, v sub x, and v sub xx, and also v, right? In other words, is these guys. Yes, this is the Black-Scholes formula. This is the delta. This is the theta, and this is the gamma. Now they have the Q here, right? Which I think you know what Q is. Q is the dividend rate, which is 0 in our model, right? So if you add up, right, minus R times this, plus, you know, this times R times S, and then plus this, right, plus this times sigma square S square, what will you get? You will get 0 analytically, right? I guess you haven't played around with this for a little bit, but these formulas do combine, all right? They do combine like that. Again, it's a bit tedious, and I don't want to, you know, make that into, I could make it into homework, but I definitely won't lecture on it. But anyway, right, you can really check out that, I mean, you did, didn't you? I mean, you did in the sense that I asked you to do that homework, right, in last week, right, where you plot the graph. I mean, the graph really comes from this formula. So if you see that the graph match, so meaning these guys must cancel exactly, right? Now, what I want to say is this, right, that suppose that you only know it's hold for the call side and not for the put side, right? By the way, right, do they really have to list out the put for you here in this chart? No, right? It's kind of redundant because you can really find it, right? You have questions, Shannon? right? Because they list it out, right? But it's redundant because why? If you have the delta of the call, right? So delta call, this is the only thing I know, by the way, is ND plus, right? Then what is delta put? Well, it should be this, I think. Why? Because call minus put is forward, which is S minus K divided by tau, right? So I might get my sign wrong. Agree? So this is put call parity. So delta call minus delta put is equal to 1. Also, it's going to be this minus 1. Agree? And what about gamma call, gamma put? What must happen? Should be. I mean, you don't have to. Yeah, but you don't have to look into your chart. Because here, right, if you differentiate on the right hand side twice, what do you get? Huh? No, Shinan, you're working too hard. Look at this. If you differentiate this twice, what do you get? 0. So therefore, gamma call must be gamma put. Right? You understand? So sometimes, right, again, I know there are formulas, but that's why you want to learn. Because when you learn, you can think about things much more easily than just staring at the tedious formula, right? I can easily know that gamma call and gamma put must be equal without even looking at the chart. Again, of course, that doesn't mean I know what gamma call is. I know they must be equal, right? What are theta call and theta put? How are they related? I think this something is like this. Why? If I differentiate with respect to tau on both sides, right? But, oh, so it's a plus, right? I mean, there's a minus sign, but it doesn't matter, right? Because you flip everything, right? So if you differentiate tau on both sides, this is 0, and this is going to be this. Oh, they are missing R. Right? Agree? Sheena is still checking my math, right?
I still have minus sign.
There's a minus sign here.
A minus, yeah, because the overall is
Oh, you could be right. Let me see, right? So but I was thinking, right? Because when you do this and you take the minus, it's the same. It will be, you know what I'm trying to say? Then the minus sign will really cancel on both sides. Because, oh, wait, hold on. You're right. I think that might be a minus. You might be right. That's a minus. Okay, thank you. Right. Thank you for keeping me honest. Yep. Anyway, right. I'm not here to check out the details, but the point is, right, these guys are very easily found. Therefore, right, therefore that if you know that something is true for some option, let's say the call, then you can easily show that it holds for the put. Why? Because the put and the call are linearly related. And this PD is linear. You understand? Well, here's the thing, right? It's very cheesy. Black-Scholes PD holds for call. Does Black-Scholes PD holds for the stock itself? You asked this question. Well, let's take a look. What's V here if it's just a stock? V will be S, because it's just a stock. What's VT? 0. What's VX? 1. What's VXX? 0. So does it hold for the stock? Of course it does, because this cancels with this. You understand? Right? The point is you could think of this very mechanically, like at the concrete level, but right, you also should think of it abstractly, right? So it does hold for the stock. Now the PD being linear, right? So it must hold for, oh, by the way, right, maybe, let me say one more thing to be pedantic. Flex shows PD holds for cash, right? Now that's too trivial, but meaning what? If it's cash, then, so by the way, right, when I say hold for stock, what does that mean? That means VT equal to ST, right? Hold for cash means VT equals to K, right? Does it hold for cash? Meaning for bond, right? Well, if it's cash, then what is this? Not really. It should be K e to minus R tau, because it's cash discounted, right? Because this is anytime. So I think it's minus R K e to minus R tau, right? You know, if you do K, then actually you only have this term and everything else is 0. So it won't be 0. You see? Right? So what is VT? VT will be exactly that. Right? And then this guy will be 0. Whoops, I should not erase it. Do you understand? So it does hold for cash, but you gotta just plug in correctly. So basically for cash, right, there is theta, right? For the cash account, there is theta, right? Because it does have time value of money. Okay. So the PD holds for cash, hold for stock. Therefore, what does it hold for? Cash. You know, what do I want to say here? Holds for, so first of all, right, it holds for stock, it holds for cash, or it holds for forward contract. Do you agree? Because what's for forward contract? Forward contract is just this. Okay, so here, right, is where I use linear. Right? By linear PD, I mean something you learn in when you learn ODE theory or whatever. Basically, it says that if you have a solution, right, then you can do combination of solution and still have solution. So basically, it says that linear combination of solution is still solution, right? And once you know it's hold for forward contract and it holds for call, then must hold for put. Because put is forward minus call. You understand the idea? Right. So I want you guys to get concrete, but not too concrete by checking out all the formulas, but not too abstract either, like this. Right. Again, there's nothing wrong with being super abstract, it's fine. But as long as you get it, it's fine. But sometimes getting it to a concrete level helps, right? To check out all these connections and appreciate the linear connection. All right. Any question on this? All right. So here's a question I want to check out. Does Black-Scholes PD hold in real life? This is something we should check out, right? But I was thinking, right? I don't know. So I know that Shinan put the Nasdaq delta on it, but does Nasdaq have theta and gamma life?
Yes,
They do.
they do.
That's good, because then I will put an extra question on how this homework. I'll put it later, right? Use Nasdaq data to check if Black-Scholes holds. Right? Why not? If we sit here and claim that all these Greeks hold in a weird way, they don't really hold, what are we talking about? I think they should hold, right? But it will be good. And it's going to be very easy, right? You just take a snapshot of those information and combine them in the Black-Scholes PD and see if they add up to zero. Or maybe not exactly zero, but must be quite small, right? All right, so I'll put that in. Any question? All right, now, then the next thing I want to talk about is working with the Greeks. All right. Now, this is something that actually I am in no position to teach you because I don't know it that much either, but I want to at least give you the message that Greeks are super important. In practice, all right? Well, why? You probably don't need to know why, right? I mean, not need. I don't need to convince you. Why? Because even Nasdaq data lists all these things. If Nasdaq lists it, it must be important, right? Or Bloomberg or whatever, right? I mean, there was this guy who gave a talk last semester. What's his name? Parth, right? He is a Greek. He's not a Greek, a risk manager, right, in a Canadian bank, right? I think Toronto Bank. He keep going on about Greeks, remember? And he's in risk. He's not even in trading. And so, right, and you can see why it's important. So basically, right, in some sense, here's the deal, right? Let me tell you, right? When a trader trades, right, you think what does he care more? The delta or the stock price right now? For a trader, right, he wants to put it in a trade. What does he care more for? The current stock price or the delta?
The delta.
Absolutely the delta, right? Because the stock price, he doesn't care how much he buys with. He cares for how much he can gain, how much he can lose by making this bet, right? I mean, you think about it, right? Somehow we get the illusion that stock price tells a story. Not really. In the trade, it's the delta that tells a story. I mean, to some extent. Of course, there are a lot of other things, right? But at least the delta, because you want to know where the stock price is going. You don't care how much it's at, right? It could be at $1, but if it goes to 2, you can buy 1,000 shares. If it's $1,000, it goes to 1,001, you can buy 1,000 shares, right? It doesn't really matter. It just the price is just how much capital you need to invest in. It's how expensive is the trade. It has nothing to do with the value of the trade itself, right? And so on with the delta and the gamma, right? So that's why, right? It's super important. Now, so as a consequence of this, I do know that in interview, they could ask you about behavior of the Greeks. So qualitative behavior of the Greeks, all right, as interview question. All right. So let's try some example. And again, right, these questions you can find on the interview books. And this could be hard if you never thought about it. By the way, right, they're like the questions I asked in the homework, but I never really pushed you, right? I asked if you observe anything. But really, right, they will want to see if you can understand the financial behavior of the option or something when something changes, right? So in some sense, they're asking you for the Greeks. So I don't know, for example, first of all, right, what can you tell us about delta of the call option? What's so special about it? Tell us something about the delta of the call option. By the way, right, you better not say anything symbolic here because you're not going to do that on the phone. So what can you say about delta of the call option? Right off the bat, I would at least convince them that you are aware of the delta of the call option. Anything?
It is positive.
Great. But that's gonna win some point, but that's not all, right? Positive and
Less than 1.
exactly, right? So first of all, it should be between 0 and 1. See, that's English. That's good. Now, then why? Why is that true? Why is that true? Now, you're not going to say, right, it's ND plus, which, by the way, everyone should know that is ND plus. And you could do that too. You say, I know a formula is ND plus. And why is that going to help? Because this is going to be a probability, right? It's a probability search between 0 and 1. On the other hand, though, this answer, even though it could pass by, it won't win you point because it doesn't explain the financial behind things. All right, so it's okay, but it won't win you point. So what's the proper answer here? Well, the answer comes from the option itself, right? Again, a trader would say that that's obvious. By the way, right? When they say it's obvious, it's not that obvious. But what that means is they have thought about it so much that it becomes second nature to them. Look at this, right? And by the way, this is again, right, where something from this class won't help, but thinking financially helps. Look at this function, right? It's going to be 0 before k, and it's going to be linear after k. Delta being what? Delta being the change of the option payment, right, when stock price changed. And delta actually means that stock price changed by 1, right? So delta really has this question, right? Delta means delta of the stock over delta S when S equals to 1. Yes, so that's what something you should also know right away, which is weird. We never think of it this way. It could be like that, right? When stock price changed by 1, how much does the option price change? And you can see, right, here, when stock price change, right, the payoff doesn't change. So it makes sense that the option doesn't change so much. By the way, that doesn't mean the option doesn't change, right? Because option price is here, we don't care about T, right? We can just worry about 0. It's discounted, right? So there's something going on with the average payment. So never forget that. But anyway, right here, if the stock price change, nothing much can change here. Here, when the stock price change with the discount, right? Here, if stock price changed by 1, that means this changed by 1. But with the discount and with the average, how much can it change by? Also 1, right? So that explains the upper bound. You understand what I'm trying to say? The lower bound is also clear, right? Because there's no place in here where the stock price go up and the option price goes down. Is it okay? So by the payoff structure, you can tell about the delta between 0 and 1. Again, right, I'm waving hand here a little bit because I'm not trying to convince any interviewer, But I just want to point you to the way that you want to think, right? To explain this to an interviewer, right? By the structure, right? By how it moves. By the way, right, if you want to be a little bit more impressive or, oh, sorry, right? In the money, right? You can say, right, when the option's out of the money, then stop price moves won't change the payoff. When the option's in the money, stop price move by 1 unit will change the payoff by 1 unit. So discount or on average, at most it can change by 1. Understand? When you say those kind of language, they will catch up and they will see that you are thinking financially. Understand? Again, right, minimize symbolic discussion. You don't want to say when ST is bigger than K, when ST is less than K. That sounds very bad on the phone. Okay. So, but anyway, right, you work on it, but I just want to point to direction that you want to explain this. Now, what's the next question they can ask? Well, they can ask when the option is deep in the money, what is delta? And the answer is, so first of all, you want to understand what they're asking for, and then second of all, what's the answer?
It's 1.
Yeah, gotta be, right? By the way, they would think this is an obvious question. They'll never be impressed if you get it, and they will be very disimpressed if you don't get it. Why? Deep in the money means over here, right? If it's over here, then this is almost linear. Then you don't really need the plus. So it's a 1-by-1, it's a 1-to-1 change. By the way, right, a student would think what? The student would think of taking the limit as S goes to infinity of ND plus, and they'll get 1. And they're like, I get it, which is fine. I have nothing against this kind of thinking. I'm just telling you that on the street, right, no one will be impressed by this argument. All right, so it's 1. Why? Because of this payoff structure. Deep in the money, this is like linear, so it's a 1-to-1 trade-off. Does that make sense? So deep out of the money, the option is, sorry, the delta is, yeah, right? Again, I'm not being pretentious, right? By saying that this is a very deep question. I'm giving you as the easiest question they can ask. All right. And there are more complicated questions that you really have to think about. For example, maybe, right? I don't know. Where is delta roughly highest and why? Where is delta maximized for call option and why? Oh, gosh, that's stupid, right? Delta is highest deep in the money. Where's gamma highest? Right? Delta is highest when it's deep in the money. Where's gamma highest and why? So what are they asking, right? They're asking for when the delta changed the fastest, right?
It's 1. The option is at the money.
Yeah, I think so too, right? It should be around this region. What's the reason? What's the intuition for why this is true? Now, I don't claim I know the answer here, right? I'm just throwing this as a question. I could try to answer like this. This is where the concavity is the highest because gamma has to do with second derivative, right? So it's a concavity. So this is where the concavity is highest. I'm not sure they'll be impressed by my answer though, because that's a math answer. All right. But anyway, right? I just want to give you something like this as right, and you would understand why, right? A trader would care where the gamma is highest. Okay. another example, right? What's so special about the Vega of call put? Anything you want to write home about for Vega of call put? Vega is always positive for either call or put. Now, first of all, right, how is Vega of call and put related? Huh? Yeah, how are they related? Yeah, I'm asking how are they related? They're the same, right? So you should know that Vega call is equal to Vega put. The reason is put call parity again, right? In the forward, right? Because the Vega forward is equal to 0, right? The forward has nothing to do with Vega, or the sensitivity of a forward contract to volatility is 0. Okay. Now, I don't know if there's any intuitive answer, right, to the why Vega of a call put is positive, but at least you should know that as a fact. Why is that important? Why is this important? Why is this fact important? Well, if a trader, right, sees this, they would know exactly why. I mean, have you heard of traders who trade volatility? First of all, what in the world does it mean to trade volatility? Can you sell me a volatility I can take home with? Obviously not, right? Volatility is not something that we can take home with. On the other hand, right, here's something that is out there in the street, right? People can trade almost anything, right? Tangible or not tangible. So I want you to be aware that when they say they trade something, all they mean is to invest, to trade in X, whatever the heck X is. So make an investment. I mean, maybe to trade here, right? You could be to take a long position in X, let's say, so that if X goes up, you gain money. That's it. And this investment doesn't have to be in X, by the way. Obviously not. If X is, air, then you cannot buy air. But air pressure, right? Or temperature, right? If you want to buy temperature, what does that mean? What that means is you want to make some investment so that if temperature goes up, you gain money. Well, certainly there's something like that, right? If you buy air conditioner, right? If temperature goes up, people will buy more air conditioner, so you get money. Understand? So that's what it means to trade in something. Of course, you short X is the same thing, right? You want a short temperature, meaning that you want to make an investment so that if temperature goes down, you get money. Maybe heat, right? Gas. So to trade volatility means you make an investment so that if volatility goes up, let's say you want a long volatility. That means that if you make an investment so that if volatility goes up, your payment, your value goes up. By the way, right, this is not that mysterious nowadays, and you guys should be aware of that because there's something called the VIX index. The VIX index, right, is some sort of like ETF, right, that exactly match the movement of the volatility, I think, of the S&P itself. So, by the way, I don't recommend this, but I think you guys should play around on Robinhood for a little bit. Don't get into it because you will lose money or something. I do not recommend it. But you want to be around there to be aware of what ETF you can buy and sell. Because ETF, right, is a crazy way to replicate almost anything, gold, market, whatever, right? So you can go on Robinhood and literally pay cash for VIX. So you can really buy volatility, okay? Because there are people behind the desk that does this for you, so you can buy directly. But let's say back in the day when this guy is not around, what do? Oh, you just buy call and put. Why? Because the Vega is positive. So buying call and put is like buying volatility, even though, right, it's not perfect. You will be, this is called the, I guess the leverage, right? You'll be leveraged by the Vega or something. But at least you can buy volatility if you want to. So for a trader, right, investing in call and put is the same as a bet on the Vega. Sorry, it's the same as the bet on volatility. Does that make sense? So, right, this is why, like, I'm not sure this will happen, but what does it mean? Let's say for a trader to say, I want to buy the delta. What does that mean? They want to buy the delta. That means they want to make an investment in something so that if delta goes up, then they make money. For that trader, what kind of Greek will matter? The gamma, because the gamma is the movement of the delta. And so, right, you see, this is why in that Wikipedia page, there are all this weird thing where they have the ultima, the dual delta, and that kind of thing. Zama. What are these? These are the Greek of Greek, right? They are the movement of the, right? This, say, the color, God knows. This is the movement of the delta, sorry, the gamma with respect to the time of duration, right? So don't get put off, right, by the math, but try to look at the financial meaning. The Zama, I think I've heard of it somewhere, right? It sounds like zombie. Zama is the volatility of the gamma with respect to the volatility. Obviously, this is important for someone who wants to trade gamma, right? This is a volatility of gamma with respect to volatility. So who knows, right? If volatility changes, the gamma will change. So they want to track this, right? So all this fancy thing, the reason why it has a name because someone somewhere cares for it, right? Not that you need to, we have a lot of things to look at. But I'm just saying that the Greeks are super important. And like I said, I'm not in the position to teach you, but you want to, right, pay attention. Okay. So last but not least, I want to talk about the idea of Greek neutral portfolio. And this has a lot to do with risk hedging. Right? So the story is very simple, right? Suppose you long a call option. Then the language will be that you're exposed to the delta risk. What does that mean? That means that if stock moves, then your portfolio value moves. Right? Now, by the way, right, you think why is that bad? So do remember, right? A lot of times risk in the financial world just means change, random change, right? Risk doesn't mean bad change. It could have that meaning too. Risk can be lost. A lot of times risk can have the meaning that it's just a change, right? So you're exposed to delta risk means that if stock moves, this moves. So how do you immunize against this risk? Well, you immunize against this risk by making the portfolio delta neutral. What does that mean? What that means is you need to hedge the risk. You need to hedge the risk, or you need to hedge by investing in something else, in extra asset, right? Well, here's very simple. So you have a call option, right? So one share of call. So what do? The idea is you will short, so you long one call, right? You short delta share of the stock. Okay, so your new portfolio will be 1V call minus delta times stock. Okay, so check the math, and it's gonna look like strange. So delta of the portfolio, right? Delta of the portfolio will be delta of the call option, right? Which is 1 minus, well, delta of this will be, because this is one share, this is S, right? So delta of this is 1. So, sorry. So yeah, sorry. What did I say here? Delta call is delta call, right? And then this also minus delta call. Does that make sense? Right? The delta here is delta call. The delta here is because this is 1. So that becomes delta call. So this is number of shares, all right? This is number of shares. Now, this math is a little bit dubious because the delta call here can also depend on delta. So when you do delta here, so when you do it, you have to keep in mind this is a constant. All right? Actually, it could change, but you think of this as a constant. So what's the idea? That if at any point, right, if you hold delta share of the stock, right, short, portfolio will not move in value when the stock price moves. So doing that means that you make the portfolio delta neutral because the delta is 0, delta neutral. Okay, sorry, we're out of time, but let me just say one thing. This idea doesn't work in the long run. Because in the long run, right? So this idea only works in short time. Right? Because in the long run, right, what happens is that suppose time moves, then the delta of the call is no longer at the original value. It'll move to something else. So basically your hash is no longer correct. So then you have to rehash by rebalance your portfolio by buying a new delta, or rebalance so that the delta now becomes correct. So you have to rebalance. All right. So you need to rebalance, and that becomes a pain because that could be right when you buy and sell, you have to pay trading what do you call it, commission. So you could do this, and you can do rebalance, or you could also take a step further and make the portfolio delta and gamma neutral. Why does that help? Because if you make it gamma neutral, then when the stock price moves, the delta won't move. Delta won't move, stock price won't move, right? So on and so forth. So we'll discuss it next time, all right? But the idea of making a portfolio Greek neutral. So basically you neutralize it against any risk you think is important, be it volatility risk, interest rate risk, whatever, right? Then you do that thing. Okay, let's continue next time.
Thank you, Professor.
Yep, thanks.